Okay, so have you ever stopped to wonder, what is a thought? I mean, really? How does the decision to just move your hand travel from your brain to your fingers in like a split second? The answer to both of those questions is actually a story. It's the story of a single tiny electrical signal that is the language of our entire nervous system. So let's dive in.
To get our heads around that massive question, we've got to think small, like microscopically small. We need to understand the biography of a single lightning-fast pulse of electricity. This, my friends, is the story of the action potential.
At its core, that's really all it is, just a super quick flip of the electrical switch inside a single neuron. But this simple little flip, it's the basis for every single sensation, every memory, and every action you have ever experienced. It is the absolute hero of our story today.
Now, every great story needs a calm before the storm, right? For a neuron, that calm is its resting state. It's not just doing nothing, though. It's waiting, perfectly balanced, just ready for a signal to show up.
And this number is its baseline. A neuron at rest holds this stable negative charge inside itself, known as the resting membrane potential, of about -70 millivolts. You can think of it like a coiled spring, just packed with potential energy, waiting for the perfect trigger.
So what is that trigger? Well, Act 2 kicks off when these little chemical messengers, we call them neurotransmitters, arrive from a neuron next door. They latch on and they start to disturb that quiet negative piece.
When these neurotransmitters lock in, they cause the neuron to what's called depolarize. All that means is the inside of the cell starts to become less negative. It begins to creep up from that -70 millivolt baseline. It's like a little nudge, then another, pushing that voltage higher and higher.
And that brings us to the single most important number in this entire story, -55 millivolts. This is the threshold. See, if the neuron's charge doesn't hit this exact number, the signal just fizzles out, nothing happens. But the very moment it hits -55, well, that's the point of no return. Because once that threshold is crossed, the neuron commits. It's all or nothing. It unleashes this unstoppable surge of electrical energy. This is the climax of our story. This is the action potential. Now, this surge isn't just chaos. It's this beautifully choreographed dance of ions moving in and out of the cell. So let's break down this rhythm step by step, starting with that crucial moment we cross the threshold. The absolute instant we hit -55 millivolts, it's like a dam breaking. All these specialized gates along the neuron's membrane just swing wide open, letting a flood of positively charged ions pour into the cell. And here's the really key detail. It's the voltage-gated sodium channels that open up first. All these positively charged sodium ions, which are normally crowded outside the cell, now have a wide-open path to just rush in. Meanwhile, the potassium channels, they're staying shut, for now. You know, this flood of positive charge is just incredibly dramatic. The neuron's internal voltage doesn't just get back to zero. It skyrockets way past it, becoming super positive. And that massive, super fast depolarization is the signal. That's the peak of the action potential that now starts its journey down the neuron.
But hey, what goes up must come down. A neuron can't just stay in this hyper-energized state forever. It has to reset before it can fire off another signal. And this brings us to Act 4, the reset.
At the very peak of the action potential, a switch gets flipped. Those sodium channels slam shut, which stops the flood of positive charge. And at that exact same moment, a totally different set of gates, the potassium channels, finally swing open. So now, the flow is totally reversed. Positively charged potassium ions, which are concentrated inside the cell, start rushing out. And as all this positive charge leaves, the membrane potential just plummets back down, making the neuron negative all over again. We call this repolarization.
Now, the potassium channels are just a little bit slow to close. So, for a split second, the neuron actually overshoots its target, dipping even more negative than its -70 millivolt resting state. This is actually a really clever built-in safety feature called the refractory period. It makes sure signals only travel in one direction and gives the neuron a quick moment to recover before it can fire again.
So we've gone from a quiet potential through this huge, dramatic surge and all the way back to rest. But why? What's the point of this entire elaborate electrical dance? Well, the answer is actually pretty simple. Communication.
This action potential doesn't just hang out in one spot. It travels like a wave all the way down the length of the neuron. And when it gets to the very end, it triggers the release of those neurotransmitters, which then float across to the next neuron in the chain.
and potentially start this whole incredible story all over again.
So there you have it, from a quiet negative 70 millivolts to a massive surge of electricity and back to rest again, all in just a few milliseconds. That's the story of one action potential. So the question I'll leave you with is this. As you're processing these very words, how many billions of these tiny, epic stories are unfolding inside your head, right this very second?